Okay, so let's get started. Hello and welcome everyone to the 10th lecture of our CUDA programming. So in the previous lecture, we saw multiple things related to the shared memory, right? So we saw how that L1 cache is divided into two components. One is the L1 cache itself, and second component is the shared memory or the scratchpad memory. And yeah, and then we saw how to okay, so then we saw like that L1 cache is managed by hardware, but that shared memory or scratchpad memory is under the programmer's control. So we can specify which variable or array should go into that scratchpad or shared memory. And we saw how to allocate variable or an array in that shared memory. Then we also saw how to access, how to load store data into that variable which is declared in the shared memory, or the array which is declared in the shared memory. Then we saw like that shared memory is per thread block, and each thread block will have the separate copy of that shared memory. And yeah, and then and after that we saw multiple programs and multiple examples related to the shared memory. uh, yeah, so there we stopped in the last lecture. So that was the outline for the last lecture. For today's lecture, we are planning to look at that synchronization construct that I told in the previous lecture, which is sync thread, which is used for synchronizing the threads within the thread blocks. Within the thread block. And yeah, so we'll see that synchronization construct. We'll understand that in detail. Then we'll see multiple examples related to that synchronization construct, which is across the thread of a thread block. And then we'll see something called as dynamic shared memory, how to allocate the shared memory when its size is known at runtime. So yeah, so how to do that, we'll see. How to allocate dynamic shared memory, we'll see. Then we'll also see how to specify the size of that scratchpad memory or shared memory, and the size of L1 cache using some APIs which are provided by CUDA. So we'll see that, and towards the end of this lecture, probably if we get some time, then we'll see what is band conflict and what are issues related to it and how it is associated with the shared memory and all those things. Yeah, so I guess that's our plan for today. So with this, let's get started. Yeah, so this was the if you will remember, this was the last slide that we saw, and we saw that this kernel, which is D kernel, can produce multiple outputs, and we saw that there are total 5 possible outputs. One is so those 5 possible outputs are 1, 2, 3, garbage plus 2, and garbage plus 3. So those were the 5 possible outputs that can be printed by this kernel, and like this. Okay, anyways, let's continue where we left off. So this was the last slide that we saw in the previous lecture. So in this slide, we saw that there is this D kernel, which which can give multiple possible outputs. So we saw 5 possible outputs, which are 1, 2, 3, garbage plus 2, and garbage plus 3. And yeah, and we saw that if we run this kernel once or twice, then we might not see any different value apart from 3. But if we run it multiple number of times, probably 20 times here as we do here, then there is some chance that we see some another value apart from 3. And yeah, so this shows that, yeah, there are multiple possible outputs, that can be printed by this kernel. And yeah, that's the brief recap of the last question that we saw. So moving on, I have some another classwork for you people. So if you can see, this code is exactly similar to this previous code that we saw in the previous lecture. But the change here is that we changed this 100 to 31. So I request each and every one of you to try out what will be the output of this code. If there are multiple outputs, then please type all the possible outputs in the chat and please try it out. And yeah, so here there were multiple possible output because of the asynchronous executions among the warp threads. So these two statements as well as this statement were executing asynchronously. Due to this, there were multiple possible outputs due to data race plus asynchronous execution. And we saw how to calculate the multiple outputs for this. But yeah, for this case, what will be the outputs, and if there are multiple outputs, then what will be those multiple outputs? Please try out and post your answers in the chat. Yeah, please try out and let me know. Yeah. Okay, Varun is saying s equals to 3 only. Yeah, 20 times. Yeah, that is correct. Since we are running this inside the for loop, which is being run from 0 to 9, and there are two blocks, thread blocks. So yeah, 20 outputs. But yeah, what will be the output for each case? So Varun is suggesting it will be 3. Okay. Vasantha is saying it's 3. Okay. Request others to also try. So
Sir, can you show the code again?
oh sure. Okay, there are just two responses. Anyways, I'm assuming that you people are trying. But okay, let us try to understand what will happen in this case. Okay, so let us understand what will happen with this code. So again, this code will, I mean, uh, this kernel will be launched 10 times and with two thread blocks during each launch. So during for each thread block, what will happen? So that for each block there is a shared variable s, and it is being updated by this three inside this with the help of these three statements, right? This, and this. So okay, and one thing to observe here is that in the previous case we had this thread ID 100 here, and this thread ID 100 was belonging to the thread which was in the different warp as compared to these two threads. So this thread 0 and thread with ID 0 and 1 were in the one warp, and thread with ID 100 was in some another warp. So due to this, there was some asynchronous execution happening, because this two statement can be interleaved with this statement, because as as you people remember from the previous our previous lectures discussion, that warp threads can be executed in any interleaving fashion, and if there is, I mean, if they are executing simultaneously, then there is also chance of data risk. So yeah, I mean, among the warp threads, I mean, among the threads which are in different warp, there can be asynchronous execution. But if you will remember, for the threads of the same warp, we have this SIMD execution, which is single instruction multiple data execution. So they will be executing in lockstep fashion. So what will happen is, since 0, thread 0 with ID 0, thread with ID 1, and thread with ID 31, all these three threads belongs to same warp. What will happen is they'll execute in SIMD fashion, that is lockstep fashion. So thread with so this will be the execution flow. Thread with so all the 31 threads, or probably all the threads of the thread block, will start executing this kernel. uh, Here what will happen is, thread with ID 0 will be entering this if condition. Rest all threads will be masked from having ID 1 to 31, and all other warp threads can execute, I mean, go further, but for them nothing is, I mean, no if condition will be satisfied, so nothing will be done. So here only one warp will be executing the statements, right? So for that just one warp, and within that one warp, the thread with ID 0 will be executing the statement as equals to 0. Meanwhile, all 31 threads of that warp are masked out. So yeah, they are masked out. Then so as value of s is initialized to 0, then they move further, and the thread with ID 1 within the same warp will do s plus equals to 1. So as s's value is 1, and meanwhile no other thread within the same warp, meaning thread from 0 to 31, except the thread 1 will move further, because will not move further because they belong to same warp, and they have to execute in lockstep fashion. So they'll be masked out, and they'll wait for this thread 1 to finish execution. Then again, once this thread 1 finishes execution, they'll move further, and now thread with id 31, which again belongs to that same work, will satisfy this condition and will make s plus equals to 2. So value of s will now be 3, and rest 31 threads with id from 0 to 30 will be masked here because they belong to same work again. And yeah, now the value of s is 3, and thread with id 0 will print that value of s. So in this case, the output which is present inside, which is the value of this shared variable s, is 3, and this output is deterministic because there is no concurrent execution happening here because of this WOP based SIMD execution, which is lockstep way of executing the statements. So okay, so here the output is deterministic, which is 3 for any case. So even if you run this program any number of times, you won't see any different output apart from 3. Okay, so that is one case. That is one thing. But let us say that we are not allowed to change. Okay, yeah. So let us come back to our original question. This one, where we had this condition 0, 1, and 100. The side is 0, 1, and 100. Now let us say that we are not allowed to change this 31 to this 100 to 31 as we did in previous case here. We want this to be 100. We just don't want this to be 31, and still we want the output to be deterministic, which is 3 for all the cases. For all the cases we want output to be 3, but we can't change this id from 100 to 31 or any other id which is within the work. Maybe because all the warp threads are busy doing something or some reason is there. If that is the case, how can we still guarantee that the output is deterministic, which is 3? So I want each and every one of you to think about it, like considering that these 3 if conditions or this entire piece of code can't be changed. These conditions can't be changed, these 4 lines can't be changed. How can we make this code deterministic is my question. Please think about it and post your answers in the chat, or either unmute yourself and you can answer. I hope that question is clear. Yeah, so I guess the previous one everyone understood s equals to 3. Yeah, that's correct. So request others to think about the question that I asked. Like, we can't change this lines, these 4 lines, but still we want the output to be deterministic, which is s equals to 3 for all the cases. Then how can we do that? Or at least some brief idea about how can we do that? Okay, so deterministic here is like I'm taking Gopal's question. So deterministic here is that we just get one output is the meaning of deterministic in this case. So we don't want the output to differ across multiple runs as it was happening here. So if you see here, if we execute this kernel for multiple runs, we can see that there is some different value that we can get. So there is this non-determinism in the output. We want output to be deterministic, meaning that it should give same value for no matter how many times you run. That is the meaning of determinism here. I hope that is clear. Let me. Decreasing the block size may reduce the fluctuation in the output. Okay, it might reduce the fluctuation in output. Okay, that is correct. But we are not bothered about reducing the fluctuation. here, Harish, but we are concerned about the correctness. So even if it is giving wrong output one time out of 100 execution, then it's, I mean, it's incorrect, right? So that is our concern here. uh, Use of atomic barriers to synchronize the threads. Yeah, I think this might be the possible solution. Would you like to would you like to add where, I mean, explain where we should add the barrier or synchronization construct somewhere in the example here?
My understanding is the way we can do the things in CPU where we can add locks. I don't know
Okay.
how we can do here. Similarly, we need to ensure that the first two statements happens first,
Mm-hmm.
and only then the first warp threads wait. All the threads wait till this the next execution
Yes, that
happens.
is correct. So we somehow need that these two threads, I mean, these two statements, or there is some sequentiality. I mean, what can I say is that this warp threads, first warp threads finish these two statements, then only all the other threads proceed to this statement. So we need something which can provide us that functionality, and we'll see how to do that. But let me quickly see. We can set a flag inside first two if condition. Use that as a condition inside the thread. Okay. I don't think that this will work, because if you remember Rishikesh, that let us understand the Rishikesh suggestion. Uh, he's suggesting that we use some flag here, and that flag is only set when these two conditions are finished execution. And if that is the case, then only execute this if condition. Okay, that is possible, but let us understand what can be the issue there. When you declare any flag variable here, in this case, uh, it should be okay. Let us say first of all that you declared that variable as not shared but just simple variable int flag. Then in that case, that is a thread local variable, and it won't be accessible. It won't be accessible across uh, all the threads. I mean, even within the thread block. So that is one thing that you can't do. Second is you can use some sort of a shared variable like this again. So that will be only set when both of these conditions have finished execution. But in that case also, I think you will need something, some check such that it can be tested and setted atomically. Otherwise, it will happen that the thread with ID 100, which is in different warp, might see that the flag value is 0 and it might not execute this statement and will go on. It should happen that so here it should be guaranteed that the value is set to that value of flag is set to true, and then only the flag with thread with ID 100 execute this if condition. If that is not case, then output 1 will also be possible. So I guess that might cause some issue, but I think that you need to refine this idea further in order to get the the output that we are desiring. So yeah, so that is one thing. Could we use CUDA device synchronize inside kernel? Hmm. Okay, I don't think that I think that we can use CUDA device synchronize, because there is one option of launching kernel from the another kernel. So I think there should also be an option for CUDA device synchronize, but I haven't seen any code. I mean, I haven't seen any example doing this thing. I mean, doing CUDA device synchronize from within a kernel. So I can't comment about this thing. So yeah, I am unsure about this, like whether we can use CUDA device synchronizer inside a kernel. So most probably the answer is yes, but I'm unsure about it, I'll say. Yeah, so yeah, that's it. So with this, let's move on. Okay, so good. I mean, you people have at least tried. So let us see what happens here. Okay, so we want to, okay, as I said, we want to uh, get the deterministic output, which is 3, even when this 4 lines are not changed. So how can we do that? So let us try to understand the way it can be done. So here comes the interesting part which I mentioned in the previous lecture, which is this sync thread. So let us try to understand what this sync thread does. So this sync thread is a sort of a synchronization construct which is used to synchronize the threads within the same thread block. So let us understand with the example what will happen. So think of it as a sort of barrier. So all the threads, all the threads within the same thread block will wait here until, not all the threads, but whichever thread which reaches here will wait here for all other threads to come. And once all the threads have arrived, then only they'll move to the next statement. So let us take an analogy here. Let us say that let us say that we plan to play football match, and in that case, what we do is we decide that we'll first of all meet at some common point at some place, or some ground. We decide some ground at which we will all will meet, and from there onwards we'll go towards some uh, bigger ground where we can play the football. So that point where we all meet, that ground, is called a synchronization point. So we might asynchronously leave our home and follow different paths to reach that common point. But yeah, once we all reach at that common point, then only we'll proceed towards our final destination, which is the final football ground where we are going to play the match. So this sync thread is something like this, but among the threads of the same thread block. So let us say that thread 1 has reached here, but all other threads which are apart from that thread 1 are still here, executing some statement here, uh, which is above this sync thread. Then this thread 1 will wait here until all other threads have reached here. Once all of those threads have reached this point where the sync thread is written, then only they'll move to the next statement, which is after this sync thread. So yeah, that is some sort of the barrier. All the threads will be, all the threads which have reached here will wait until all other threads uh, have not made up till this point. Any questions till this? For this sync thread part, then quickly I'll look into the. Okay, there is some question. Can we pass argument to pause some set of threads in what? I didn't understand your question, Ramasam. Can you elaborate?
Yeah, in sync thread,
Okay.
can we pass some arguments so that some specific set of thread I want to delay or pause something like
Okay, till now I haven't seen any argument being passed to sync thread such that we want only uh, some of the threads within the thread blocks to synchronize. But okay, I'm not sure about this, but I mean my best hunch is that there is no such arguments possible here. But I need to check whether it is whether it is the case or not. Yeah, so I'll say that I'm not 100% sure, but that is what I think that it is not the case is the answer to this question. Okay, anyways, there is some question, sir. How would sync thread work inside a if? Okay, yeah, if that's a good question. Let us understand how sync thread would work inside an if. You might remember that one of that slide that we saw during computation, right? There in that slide we had that global barrier, if you remember, inside if, and we saw what happened in that case. There was a deadlock. So something like that will happen if you place the sync thread inside the if condition, and not all threads are not, if all threads are not entering inside that if condition, and you are placing that sync thread inside that if condition, then there will be a deadlock. I hope that's clear. If some threads have moved past the if already. Yeah, in that case also there will be a deadlock. I hope that's clear. I guess we have already seen one example in that computation lecture where there was some global barrier that I used to talk about. Okay, anyways, let us understand this. Okay, so we understood what is sync thread, and important point to understand here is that this is a barrier across the threads in a block. So all the threads within the thread block will only wait here. So if there is some thread which is not part of that particular thread block, then it will just move on. It won't wait here for the other threads to come to reach at this point. But if there is a thread within the thread block, then then it will reach for all other threads to reach. Reach at this place, and then they'll move ahead. So yeah, important point is it's a barrier across threads of the thread block. And again, yeah, so this is the barrier across the threads of the thread block. This shared memory is also for the threads of the thread block. And yeah, so yeah, that are the 2 points that I want to specify. Apart from that, this s equals to 0 and s plus equals to 1 are done by the threads of the same warp, while this s plus equals to 2 is done by the thread of some another warp which doesn't belong to this uh, this uh, this thread which is sorry, this threads which are in the different warp. And this printing is again done by the uh, thread 0, which is not part of the which is not inside the warp in which this thread 100 is there. And yeah, and again we are launching the kernel with 2 blocks. So yeah, that is the scenario here which is happening. Okay, so with this, let us try to understand let us try to understand what is the execution flow of this program as we saw for the previous example. So let us understand what will be the execution flow for one block, right? We are having we are launching kernel with 2 blocks, and that to 10 times, so 20 launches. 20 blocks are there total. But let us understand what will happen for just one block. And yeah, let us simulate. Let us try to understand what will happen. So here shared variable is declared. Yeah, shared variable is declared. Then all the threads of the same block will come here. They'll. Okay, first of all, let us, for the sake of simplicity, let us assume that this block size is 1024. If that's the case, then there are 2 blocks, each with 1024 threads. So within, so for one block, there are 1024 threads, or 32 warps total, and all the warp threads will start executing this code. So they'll execute this asynchronously. Warps will execute these things asynchronously, and all the warp threads will wait here. But the threads of the first warp, they'll be masked out here, right? Because 0th thread, which is the part of the first warp, is executing this s equals to 0. Meanwhile, all other threads are masked out. All other threads meaning the threads of that warp. So thread with ID 0 is here executing. All other threads having ID from 1 to 31 are masked out here. And meanwhile, all other threads of the same block are waiting here. Please note that all other threads within the same block are waiting here. Thread 0 is executing this, and thread 1 to 31 are being masked out here. Once that is finished, this execution is finished, threads from 0 to 31 will reach this sync thread statement. So as now all the threads within the thread blocks have reached here. So okay, 0 to 31 were here, they came here, rest all were already waiting here. So okay, so now all the threads within the thread block have reached here. So now they can proceed, right? Because it's only barrier across the threads in the same of the same thread block. So since all threads within the same thread block have already reached here, they can now move forward. What will happen is thread 1, okay, here what will happen is again thread with ID 1 will execute this statement. All other threads of the same warp, meaning thread 0 and thread 2 to 31 will get masked out, and rest all threads of different warps will again wait here, right? They'll wait here. Yeah, they'll wait here, and once this statement is being executed by thread with ID 1, all other threads of the same warp as well as the thread with ID 1 will move ahead and will come here. And since now all the threads of the same thread block have reached this statement, they'll again move ahead and they'll come to this if condition. They'll see that this statement is true only for the thread with ID 100. So thread with ID 100 will be executing this statement. Meanwhile, all other threads of that warp in which this thread with ID 100 is there, they'll be masked out. And all other threads of other warps, apart from the warp in which this thread with ID 100 is present, they'll be waiting here for other threads to reach this. Other thread meaning the thread within the warp having this ID 100. So they all are masked out here and thread with ID 100 is doing this statement. So other threads are waiting here. So once this is finished, they'll reach here and all the threads again have reached, all the threads of the block have again reached this point. So they'll move ahead and thread with ID 100 will print the value of S. So if you see at each and every point we have this synchronization construct and they are again executing in lockstep fashion. And if you see here, the flow of execution is very deterministic. So it will never happen that it will never happen here that S equals to 2 is being executed simultaneously with either of these two statements as it was happening for this case, if you remember. Here S equals to 2 can execute simultaneously with S equals to 0 and S plus equals to 1. But here, if you see, because of this synchronization construct, the execution is flow of execution is very deterministic. This will happen, then this, and then this. Even if they are executing we have the threads among different warps which are executing this statement. But because of this sync thread construct, they'll execute in a very deterministic fashion, and the output will be always be 3 in all the cases, no matter how many times you run this code. So I hope you are getting this point. But if there are any questions up till now, then you can shoot them on chat. Okay, I guess this one I took. Sir, how would sync thread work inside a? Okay, I also took this question. Is sync thread for a thread while? Is sync thread for thread block while global barrier for all the threads of kernel? Then can we think of global barrier as GPU version of? Yeah, first question is, first thing is correct that you are thinking, like sync thread is across the threads of the thread block, while global barrier is across all the threads of the GPU. That is correct. The second point is, then can we think of global barrier as GPU version of CUDA device synchronize? Yeah, you can think in that way, that it's somewhat similar to CUDA device synchronize, but for the GPU threads. In case of CUDA device synchronize, CPU will be waiting for the all the GPU threads to finish. But for global barrier, any of the GPU threads, any of the GPU thread across, among all the threads, will be waiting for other threads to reach that point. So that is something called as global barrier, very similar to sync thread, but across all the thread blocks and across all the grids. Think of it like that. And we'll see how this global barrier works in the upcoming lectures. Yeah. Any doubt apart from this? Okay, I think there are no other questions. Then in that case, let's move ahead. Okay, so now I have one question for you people. Okay, so the question is this. Let us say that thread 0 of one block is, okay, first of all we are launching the kernel with 2 blocks, right? So we have 2 blocks. So can it happen that thread 0 of block 0 is executing this statement while thread 1 of block 1 is executing this statement? Is it possible? Okay, I repeat my question. Since we are launching the kernel with 2 blocks, can it happen that thread 0 of block 0 is executing this statement while thread 1 of block 1 is executing this statement? And please note that we have this sync threads at every place. We have not removed that. Is this possible? The thing that I asked, please think about it and post your answers in the chat. Okay. Varun is saying yes. Request others to also think. I'll just quickly switch to the slide so that others can see the code and think about it. Okay, thank you. If Gokul is saying it shouldn't be possible because same warp threads, right? Okay, we'll see we'll see the reasoning behind it. It's possible since there are no synchronization between threads of different blocks. Yes, that's correct. With the proper explanation, it's the correct answer. Yeah. Shri is saying yes. Okay. Since there are since you people have tried, let us switch back to the slides and understand that whether it is possible or not. So short answer is yes, like it is possible that thread whenever the thread 0 of block 0 is executing this statement, thread 1 of block 1 might be executing this statement. And why is that the case? Because if you people understand this sync thread properly, then this sync thread is only the barrier across the threads within the same thread block. But if you take two threads which are inside the which are inside the different blocks, which is here, which is the case here, two different blocks, and thread 1 is thread 1 is in the block 1 and thread 0 is in the block 0. If that is the case, then this thread 1 which is in block 1 will not wait for the thread 0 which is in block 0 at this sync thread at this synchronization point, because they are in the different warps, different blocks, not warps, they are in different blocks, and sync thread is only the synchronization barrier across the threads within the same thread block. So thread 1 will not wait here, it will just go on. So yeah, the answer is yes, and yeah, it is possible because of this reason, that sync thread is only the barrier across the threads within the same thread block. So I hope it's clear. If you have any question at this point, then please feel free to ask and discuss the reasoning that you have. Yeah, so by the way, the output will be very deterministic in this case, which is 3 for any 3 for any case. Any number of times you run this code of this kernel, the output will always be 3 if you add this sync threads. Questions? Okay. Okay, I guess there are no questions. Okay, then let's move ahead. Okay, I have one more question, one last question for this slide. My question is, can we remove this first sync thread, is my question. If we remove this first sync thread, then will it be the case that we get some non-deterministic output? Non-deterministic meaning any other output apart from this 3 that we are getting. If we remove this first sync thread, is there the chance that we get some another output apart from this 3? We are just removing this first sync thread. Rest 2 are still there as they are. I hope you got the question, and please think about it. Okay, I think Gokul is saying no. Shri is saying no. Varun is saying yes, because first two threads are within same warp and they have automatic synchronization. Okay, I didn't understand the connection between the answer yes and the reasoning, Varun. Like, you are saying that there is automatic synchronization.
First two, yeah, the first two statements have synchronization, at least for the first warp. So if we think
Yes.
the 100th thread anyway doesn't go through this statement, and it can wait after the first two statements has executed. So the first sync thread is not even needed for the 100th thread index.
Okay.
But for the first two thread index, as far as it is concerned, it executes in lockstep fashion. So if we have sync threads, if we don't have, in both of the cases, S will be 1 and it will just stop at that point. And for 100 thread ID, it will anyway stop at the second sync thread. First is not needed in that case.
Okay. I got it. I mean, so I think your reasoning is correct, and answer is also correct. Like, this first sync thread is not needed. This is redundant. The reason is the one the Varun explained. Like, since this thread, thread 0 and thread 1, which are the part of the same work, and since they are the part of the same work, they are executing in lockstep fashion. So s equals to 0 will be executed by the threads of the first work. I mean, not threads of the first work, but 0th thread of the first work, and rest all threads will be masked out. Meanwhile, all other verbs may proceed, but they won't execute this statement, neither this statement. So they have to wait here. Even if this sync thread is not there, they'll eventually wait here at this sync thread. And all other threads, I mean, all other threads of the first verb will move ahead only after the thread 0 of that verb has finished this statement, execution of this statement. Then they'll move ahead once this is done by the 0th thread. So first verb will come here. They'll see that thread 1 has to execute something here. So they'll thread 1 will execute. Meanwhile, others will be masked out. And please note that at that time, all other verb threads apart from the first verb, all other verbs are waiting here. And once s equals to 1 is done, then the first verb will reach here, and then the entire execution is same as we saw earlier. And if you see, if we follow this execution flow, then again the output that we'll get is deterministic, which is 3 again. So first sync thread is not needed because of the lockstep execution. I mean, lockstep execution, the way that verb threads execute is lockstep. I mean, it's lockstep way of executing, and due to that, we don't need this first sync thread. So I hope that's clear. So yeah, this first sync thread is redundant, and even if we remove it, the output which is 3 will be deterministic in all the cases, even if you run it any number of times. So yeah, please, I mean, if you try running this program by removing this sync thread, then also it will give same result, and deterministic output will be there. I hope that's clear. If there are any questions, I'll take quickly. It could be that the block 2 s equals to 0 could execute after block 1 s equals to 1. Could that be the block 2 s equals to 0 execute after block 1 s equals to 1? Yeah, I mean, it's possible, completely possible. So you are telling that block 2 s equals to 0 executes after block 1 s equals to s plus equals to 1. It's possible, right? Because if two threads are in different work, then any order of execution is possible. I hope that's clear, Gokul, because they are inside the could the above situation happen? Yeah, I mean, it's completely possible that this will happen. I hope that's clear, because if two threads are within different blocks, then there is no restriction in the way they execute. They are completely asynchronous. So anything can happen. Any order of execution is possible. Okay, I hope that is clear. And if there are questions, you have any questions further, Gokul, then please feel free to ask. But yeah, I'm assuming that it's clear, so I'm moving forward. Okay, so let's move ahead, and let us try to predict the output of this program. So okay, so first of all, I'll like to ask you people, what will be the output of this code? So here we are launching the kernel with 10 blocks, and each block of block size, and assuming that block size is some number greater than 32, which is we are launching a block, 10 blocks, each having more than just one verb of thread. Having multiple blocks in other, multiple verbs in other sense. So 10 blocks each having multiple warps inside it. We are launching the kernel, and then we are declaring some shared memory, and then we are doing some computation, and then we are printing some string which is here. We are printing it here, and yeah, this is what will be, this is where the output will be generated. So I want you people to think about what is the what is the possible output for this program, or is there any issue that will happen, or what will be the output, or is there anything that we should add here or something? Please think about it and post your answers in the chat. Okay, yes. Okay, clear. That's good. I'll probably switch back to the slides. Let me go. Yeah, I'm hoping that you people are trying. So I'll wait for few more seconds here, so that you people can get some more time for trying, and after that we'll discuss what can be the possible output, or what can be the possible issue with this code, or output with this code. Gokul has typed something 65, 66, 67, 68. Okay, I guess you are trying to print the ASCII values after A, B, C in that order. I am supposing that, like, ASCII value of A, B, C, D, and so on. Okay, let us see what will happen. So I am hoping that you people have tried, but with this, let us understand what will happen with this code. So yeah, let us see what will happen. So actually there is one issue with this code, which is actually there is some bug with this code. So let us understand what is that bug with this code. So yeah, let us understand. So we are launching the kernel with 10 blocks, each block having multiple warps. So that's fine. So here now the kernel is launched, and here what we are doing is we are initializing. We are declaring a shared array, which is character array of size block plus one. So okay, so block plus one size, and block size is some greater than 32. So let us assume that, let us take some random number. So let us say that block size is 128. So we are declaring the shared, we are declaring the character array which is shared across the threads of the thread block, threads of the thread block, and its size is 128 plus 1. Since we assume that block size is 128, so it's of it is of size 128 plus 1, which is 129. Now each thread here is writing to its own copy of the shared array. If you see here, we are using thread id x.x, and this id will be unique for each thread of the thread block. So each thread is writing to the separate memory location inside this str array, and what is it writing? It is writing something. Let us assume that it is writing some character based on this some equation, but let us not bother about what that character is for now. So it is doing some writing here in its local, in its some memory location, which is different for each thread because this ID is unique. After that, after this writing is done, each and every thread will move further ahead, or yeah, they are executing asynchronously, so they move ahead, and here thread with ID 0 will execute this. Will satisfy this if condition and will execute this statement, which is str of block size equals to /0, which is end of the string character, and yeah, so end of the string character is placed at the last position in the array, if you see in this character array. And then the thread 0 is writing, is printing this entire string or this character array. So what can be the issue with this code? So you should observe two things here. First of all, there is writing happening here, which is being done by all the threads of the different warps. So threads of first warp are writing something, threads of second warp are writing something, and so on. That is one thing. That's first thing that you should observe. Second thing that is happening here is thread with ID 0, which is the part of first warp, is printing something. So if you see this writing and writing and reading pattern. So printing is some sort of reading, right? We are reading this value of str and then dumping it to buffer, and then it is printed. So here writing is happening and here reading is happening. So if that is the case, then what might happen? What can possibly go wrong here? So what can go wrong is that let us understand with the example what can go wrong. So let us say that thread with first warp. Let us consider the entire first warp. So first warp might finish execution of this statement, this entire statement. It might move ahead. It might also enter this if. So when this first warp checks for this if, thread 0 will execute this, rest all will be masked out. So let us assume that this first warp also finished this, this if condition, execution of this if condition. Then first warp also came here and started executing this. Meanwhile, all other warps were here at this statement, and they have not finished executing this statement. And during that time, when the other warps were still executing this, first warp, thread 0 of the first warp printed this thing, str. If that is the case, then what will be the output? Well, the output here will be garbage. First 32 elements will be correct because the threads of first warp execute in lockstep manner. So this statement will be executed, and the values from 0 to 31 will get correct character values as per our computation. Then they'll move here, and print. So first 32 characters will be correct, but rest other characters which still are being computed here and whose values are not yet placed in this str array, they are not, they are not, they will not be reflected correctly here. So there will be first 32 characters which are correct and rest all might be garbage. So this is one of the possible output that can happen. It might also happen that the first warp is the last one to execute this statement. In that case, we can get correct output. But if the first warp executed all these things and came here and printed this, and meanwhile others are still here, then in that case it might happen that the value, the character array that we are printing might give just first 32 values as correct, rest all are garbage. And yeah, that is the problem with this code, that it might not print the output as we are computing. So that is the bug with this code. And okay, I'll ask you people, how can we resolve this bug? If this is the bug with this code, then how can we resolve this bug is my question. I'll quickly switch to the chat. If there are any questions, please feel free to ask. So Varun is asking, null character can be overwritten with other character? Varun, can you put some more light on this statement? How can null character be overwritten with other character?
So for the block size, we are assigning null character in that, right? But
Yes.
the thread ID corresponding to the second verb, the first thread, uh, the first, like the 32 32nd thread can execute the first statement
Okay.
and assign the value at that point. And so the null character will be overwritten, and so
But okay, but why are you assuming that null character can be overwritten? Block we
because
are yeah, please go ahead.
Block size plus one only we have to have. No?
Sorry, can you repeat?
the thread index.x in the first statement can be 32, right? If assuming block size is 32.
Yes. Yeah, but block size is 32. That is correct. Let's say block size is 32. Then thread id x.x will have value from 0 to 31, right?
Mm-hmm.
So even the last thread will write to 31 location, and this array is of size 32, which is from 0 to 32. I mean, is of size
Understood.
33. Values going from 0 to indexes going from 0 to 32. In that case, str of block size will set str of 32 to null character. So it won't happen that overwriting will happen. Overwriting of /0 will happen. I hope that you are getting this. But if still there are any further clarifications needed, then please let me know. Yeah, I mean, if there are any further clarifications needed, then let me know. I'll make it more elaborate if possible. Okay, Gokul is saying sync thread. Okay, sync thread, but where should we place sync thread? Vasantha is saying placing sync thread before the first if condition. Okay, first if condition here you are saying. Okay. I think that should also work. Okay, I request others to also think, but yeah, before printing, I think this will also work. Yeah, let us see what will happen. Okay, so the way I've done is like we can. Okay, so way I've done is like we can place this sync thread before this if condition where printing is happening. So what will happen? I mean, as we saw that all the threads, all the threads might be executing this statement, and meanwhile the 0th thread might end up printing this. So in order to avoid this, we need to separate writing and reading. Writing is happening here, right? And reading is happening here by some barrier. And this barrier is sync thread in our case. So it can be either here or here. After this if or after here. Before this if or before this if. We can place it anywhere. So if we place this sync thread, then let us see what can be the execution flow. So let us assume that earlier scenario where threads first warp was coming here and printing this string, and it was printing some garbage value apart from that first 32 characters. So let us take that case itself. So and let us understand what will happen with this sync thread. So first work, let us say that it executed this, it came here, it set the value of it set the value of the last entry in this character array to /0, and then it is forced to wait here, right? It can't just move ahead because all the other threads of different works which are within the same block are still executing this part. So it will wait here for all other threads of the same thread blocks and different works to finish. So if that is the case, then all of the threads of the different warps will finish this thing, right? This execution of this thing, and then only they'll move ahead. And once they reach here, all the threads of other warps reach here, then only the first warp or the threads of first warp can move ahead. And if that is the case, then the other threads of different warps have already finished writing, right? Here writing thing is finished. And if that is true, then if the thread 0 of first warp prints this, then I mean, we are sure that it will not print any garbage value, and the value which will be the values inside that character array which will be printed will be the value which we have computed and placed here. So adding this sync thread ensures that we'll get the correct output as per our computation. So I hope that's clear, but if still there are any questions, then we'll quickly move to the chat. Okay, placing sync thread before the first if is okay, before printing is also okay. Okay, any questions so far related to this slide or any previous slide?
I didn't catch fully. So you were saying that there will be 32 things printed always, right? Because we are always assigning the 32nd value as null character. So
okay, so I guess there is one confusion here. Please wait. This block size can be arbitrarily large. I mean, it can go beyond 32 also. So that's one thing that you should note.
in that case, what I was saying earlier, the thread index.x, the 32nd value for the str, it can override the null character, right?
How can it override? Let's say you have a block size of 32. Let us understand this. Let us
In case of 64, can we consider like 64?
Yeah, okay. Let us consider that this block size is 64, right? Then in that case, what will be the size of this character array? 64.
64, sorry.
64 plus 1, which is 65. Okay. Now what will happen? This each thread, which has their ID going from 0 to 63, will set some value inside this shared character array, right? And this values that will be set will only be from the entry 0 to 63. Do you agree with this?
Yes, but it's possible that 0 to 32 executes this statement first, right?
Okay.
Rather than other things are waiting and not starting to execute this because they are in the different work.
Okay, that's fine. I mean, if 0 to 32, I mean 0 to 31 threads are executing this, then how can this overwriting can happen is I'm thinking.
Oh, block size again I imagined as yeah.
Okay, I think you are confusing with this block size. So this block size is if you are taking it as 64, then here it's 64, and the 0th thread will always initialize str of 64 to this null character.
Understood.
So okay, let us make it more clear. If I so what will happen is that let's say that size of s was 65, right? Now 0 to 31 threads, let's say, executed here, and then they moved on, and then they made this. So okay, so as of 0 to 31 is initialized. Okay, some init value, some that computation that we did, let us assume. Then what the 0th thread is doing, it is setting s of 65 to that slash 0. And then what is happening is s of 32 to 63 is doing some init. So it will never happen that this 65 is overwritten in any case. Let us say even if you jumble these three orders, this order of these three statements, it will never happen that slash 0 will be overwritten, because there is only one thread which is writing to the 65th memory location, and that is the thread 0 here. I hope that's clear, but if still there is confusion, then please feel free to ask. Go back to chat. Okay, I'm assuming that there are no further questions. Okay, in that case, let's move on. Okay, so one thing is, if the block size is less than 32, then we don't need this sync thread, right? because if block size is less than 32, then we have just one warp, and if that is the case, then this all the warps will execute in the lockstep fashion. I mean, all the threads within the warp will execute in lockstep fashion, and yeah, all the threads within the warp will execute in lockstep fashion, and there will be no need of sync threads, because anyways the execution is in step-by-step manner, and we are sure that this printing will always be done after all the threads have finished this execution of this statement. So writing is always done before reading. Is that we are sure about if the block size is 32, because of the SIMD execution of the warp threads. But if it is greater than 32, then we need sync thread for sure, because among the threads of different warps, there can be any arbitrary interleaving of the arbitrary interleaving of the executions. Arbitrary interleaving uh, of the arbitrary executions that can happen for the statement. So in that case, we definitely need this sync thread. But if it is less than 32, then we don't need any sync thread. Yeah, so that's it. With this, let's move to our next slide, which is about this L1 versus shared memory. And in this slide, we will understand how to specify the size for the shared memory as well as the L1 cache. So there is this API called as CUDA device set cache config, which is available as part of this CUDA library, in which we can specify the in which we can specify the amount of size that we want for the L1 cache or the shared memory. And its typical syntax is this CUDA set device config, which is the name of the API or the function. Inside that, we specify the kernel name, kernel for which we want the size to be configured, and then the parameter. So this parameter decides what amount of memory we want to reserve for the L1 cache and what amount of memory we want to reserve for the shared memory or the scratchpad memory. So kernel name is the name of your kernel. Yeah, and the parameter can have three values. One is CUDA func cache preferred none, and second is L1, and third is shared. So let us understand what these three mean. So when you specify CUDA cache prefer none, CUDA func cache prefer none at this place here, what will happen is that the compiler will automatically figure out the amount of share. It will automatically figure out the amount of space needed for the shared memory and the L1 cache. So it might do some. It might do some pass through your one pass through your kernel, and might decide that okay, based on the code that kernel code that you've written, you might need some 16 KB of shared memory and 48 KB of L1 cache, or it might decide that you might need 32 KB of shared memory and 32 KB of L1 cache. In that way, it might allocate. It might do the partitioning for that entire L1 cache. So it's completely upon the it's the completely responsibility of the compiler if you specify this the way the partitioning is done. But if you specify this parameter as L1, then what will happen is 48 KB of space is reserved for the L1 cache, and 16 KB is reserved for the scratchpad memory or the shared memory. And please note that the entire size of that L1 cache is 64 KB. So this partition that you do, it should, the addition should become 64. So 48 for L1 and 16 for shared memory will make total of 64 for the entire L1 cache that we have. So that is what will happen for L1. 48 KB for shared memory, L1 cache, and 16 KB for shared memory. Opposed to that, when you specify the this parameter as shared, what will happen is that compiler will allocate 16 KB for L1 cache and 48 KB for the shared memory. So that is how that allocation is done based on this second parameter of this API or this function. And yeah, from okay, now onwards you can also now the CUDA also provides the facility to make two equal partition of this this entire L1 cache, that is 32 KB for L1 and 32 KB for shared. And if you want to achieve this thing, then you need to specify this CUDA func cache prefer equal. So apart from these three, this fourth alternative is also possible for this second parameter. So any questions till this point? If there are any questions, then please feel free to post them on the chat, or you can unmute yourself and ask. Okay, I guess, I'm assuming that you have understood things up till this point. If that's the case, then let's move on. Okay, so this is one typical example for this this function CUDA func set cache config. So here what we are doing is we are launching this kernel d-kernel here, but we are specifying the amount of shared memory and L1 cache we want for this kernel a prior. And how we are doing, we are using this CUDA set cache config function, and inside that we are specifying this thing, right? This for the parameter second parameter, we are specifying this CUDA func cache prefer L1. So what it will do is, again, as I specified earlier, it will allocate 48 KB for the L1 cache and 16 KB for the that scratchpad memory or shared memory, and then it will launch the kernel. And here we are allocating the data, which is an array of some block size, and it's shared. So yeah, it's it's shared, so it will be allocated on that scratchpad memory, which has 16 KB of size. And then we are doing some computation here. That's okay. But one thing to observe here is that let us say that you have specified this, right? CUDA func cache prefer L1. So it will allocate only 16 KB for the scratchpad memory, right? So if that is the case, then the size of array that you are declaring here, if it exceeds, then the amount of memory required for its allocation exceeds than 16 KB, then compiler will give some compile time error that, okay, you are asking for more space than what you have, what you need, that you have specified here. So in that case, you need to be careful and specify, if your kernel is taking more scratchpad memory, or need more scratchpad memory, then you need to specify CUDA func cache prefer shared, because in this case it will allocate 48 KB for shared memory and 16 KB for L1 cache, so that even you can specify one larger arrays on the shared memory and do the computation accordingly. So that's one thing. And yeah, and if you want to allocate more if you want to allocate very large array, which is again, which is beyond the size of the L1 cache itself, which is even beyond than 64 KB, then you need to you just can't allocate such big array on the shared memory, because the size is limited, which is 64 KB. So you need to allocate memory which is as much as possible on the shared memory, which is up to some extent, which is up to some size. And then once the processing is done for that chunk of the array, you need to evict that array and bring the fresh value inside the fresh value from the global memory into that shared memory, and then process it. So you need to process it in form of chunks. If the size of the array is much, size of the data that you want to process is much greater than the size of the L1 cache itself, which is the 64 KB size. So yeah, I hope this point is clear. Any questions? Okay, I'm assuming that there are no questions. Then let us move on. Okay, so let us understand this thing, which is dynamic shared memory. So if you see up till this point, the shared memory, the way we were declaring the shared memory was like this, right? We were declaring this, declaring this array, and then this size of the array using some block size, and this block size is the constant, right? Because we were using that hash defined, if you remember, we are using some hash define some value. So this value is known as compile time, right? So compiler will simply, even preprocessor directive will simply replace this block size by that value here, and the compiler will know the size of the shared memory at the compile time, right? So that is one thing. So that's okay. If that's the case, then compiler can, okay, I want to allocate this much memory at the compile time, and that is not the issue. But let us say that our requirement is slightly different. We want to allocate the size of the shared memory based on some input that is provided by user. And if that is the case, let's say we want to take some input value from the user, and based on that input value, we want to declare the size of the shared memory. If that is the case, then how can we do that? And for doing, for such kind of requirement, we need to use dynamic shared memory. And let us understand how to do that. So yeah, when the amount of shared memory is required, shared memory required is unknown at compile time, which I talked about. We need to use the dynamic shared memory. And for doing that, we'll use the third parameter of the kernel launch. And let us see how to do that. Okay, so this is the typical example for the dynamic shared memory. And if you see here, first thing to observe is that we are using the third parameter in the kernel launch. Till now we have just seen kernel launch with just two parameters, first and second. But here we are using some third parameter. So let us understand what is happening here. So first of all, we are declaring this variable n, and we are scanning this value. So this value will only be available at runtime when the user types something or gives some input to the keyboard, which will be stored inside this variable n. So, and this value will only be available at runtime. So based on this value of n at, which is available at runtime, what we do is we specify to the compiler that I want the amount of shared memory to be allocated on the kernel equal to n into the size of it. So I want this much memory, this much amount of memory to be allocated for the shared memory. So we need to specify it as the part of the third argument to the kernel call. And yeah, that is one thing. And inside the kernel call, we need to take care of one more thing, which is while declaring the shared memory using underscore underscore shared underscore underscore keyword, we need to add one more. We need to precede it with one more keyword, which is extra, which says that this is not. I mean, this size of this shared memory is not determined statically. It is dynamically determined based on the value which will be provided by some runtime entity, and yeah, based on it, the size of the shared memory will be decided. And if you see, we are not specifying any size here. If you observe closely, here we are not specifying any size. It is completely based on the runtime value that user will provide here, and based on that, the size of the shared memory will be decided. And rest all of the things are same. We are doing the computation as we did in the previous case. Okay, so any questions on how, I mean, on this allocation of the dynamic shared memory so far? I think there is one question. Sir, why do we no longer use return 0 in the main function? Is it not necessary? Okay, I mean, it's just, I think here we have used it, but I mean, it's completely dependent upon the compiler. I think some C compiler, I mean, some C compiler are strict about this, like you should return 0, otherwise they'll give some compile time error. But few of the C compilers also, I mean, we can also specify void main and then return nothing, and that's okay. But I don't think that that will cause any issue here, Harish. So is it not necessary? I mean, I think it's, I mean, I won't say that it is not necessary. I mean, you should return, if you are specifying int main, then you should return 0, is what I'll say. And I have not tried return, I mean, specifying void main and then returning nothing with nvcc. So I'm not sure if that will work, but in most of the cases, the specifying int main and return 0 is okay. Otherwise, I think if you write void main and return nothing, then what will happen is I'm unsure about. But okay, I think you should check this. If you just don't, I mean, just specify void main and just don't return anything, and compile the program with NVCC compiler and check out what will happen, Harish. So yeah, I'm not sure about this part, but please look into it. Have you ever seen dynamic shared 2D array? Okay, I haven't seen any application of dynamic shared memory to 2D array. I have seen with 1D array so far, but yeah, I have not seen with 2D array. But if you want it to be 2D, then I guess you can still do it. I mean, let's say you specify the size as n, and here you declare 2D array. Here using double braces, and I think that should work. But see, I haven't seen such an application so far, so I can't. I can't tell you. I mean, I can't tell with 100% surety that it will work. So you can try here specifying size as n, and then double square brackets here, and see if it is compiling. Ideally, it should allocate n into n, but I'm not sure if it will work or not. It might also give compile time error, so I'm not sure. Okay, it sounds like a nightmare. Can you elaborate how? I mean, how it might cause some trouble? Gokul, would you like to elaborate on that issue? Okay, I think okay, in that regard, we can use CUDA malloc in kernel. Yeah, CUDA malloc is okay, but the thing is, CUDA malloc will allocate the memory in the global memory, which is the DRAM of the GPU. But this shared thing will allocate the memory on the L1 cache. So there will be some performance benefit that you'll get by declaring it on L1 cache. But anyways, I haven't tried this, the thing that you are specifying. This allocation of 2D array in the shared memory. So I'm unsure about what will be the result. Either it will be compile time issue or runtime issue, or even some other issue. I am not sure about this. I need to see this. Okay, thanks for checking this thing. That NVCC compiler, it says the main function must be int. Return type of the main function must be int. Okay. Anyways, as I told, like I haven't seen any program so far. For all the CUDA programs that I have seen so far, it always have that int return time for the main, and then they return 0 inside the main. So yeah, it might. It's very likely that it should give error. So yeah, thanks for checking out that. So with this, let's move further. So let us see one more application of this dynamic shared memory. Let us say that you want to allocate the shared memory based on the size of some based on some value that is provided by the user, as we did in the previous case. So we're declaring this int as z, the same way in which we declared n, and then we read that value from the read the value from the user and stored it in the n. In the same way, here we are using sz, which is being taking the value and storing it. Taking some value from the user and storing it inside the sz. Then what we are doing is we are launching the kernel here, and we are passing this third parameter in the kernel call, which is sz into the size of int, which says that I want to allocate the shared memory dynamically of size sz. Sz into the size of int, which is the sz integer characters I want to allocate for the shared memory. And then I'm also passing two additional parameters, which are sz and sz by 2. So yeah, it's based on this sz. The sz by 2 value will be computed and will be passed. So here in the kernel, sz is stored. Sz is stored in the variable sz again here, and sz by 2 is stored in the variable n1. and then we are declaring this shared memory, shared array S, which will be of size z into the size of int. And then what we are doing is we are splitting this array S into two sub arrays of equal size. So how we are doing it? Let us see. So we are declaring two pointers S1 and S2. So the first pointer will point to the starting address of this shared array S, which is given by S itself, and the second pointer is pointing to the entry which is just after the half of that S array, which is given by N1. So N1 will N1. So please note that value of N1 is SZ by 2, and when we do S plus N1, we are actually skipping first half of the element. So pointer will be jumping accordingly, and the value of S2 value of the S2 will the value which will be stored inside the S2 will be address of the location which is just after the first half of the elements in the array S. So yeah, so one pointer is pointing, this pointer S1 is pointing at the start of the shared memory, second pointer S2 is pointing at the middle, and element which is in the middle of the this shared array S. And once that is done, we can use this pointers S1 and S2 to add the values the way we want using all these commands, all these statements. And yeah, that is how we can bifurcate the shared memory, which is allocated dynamically into two parts, and use both halves in the way we want. So I hope this is clear. If there are any questions, then please post them on the chat. Any questions up till this point? So I'm assuming that there are no questions. Okay, in that case, let's move on just to next slide. So let us try to see what is this bank conflict. So let us just briefly touch upon bank conflict for today. We'll probably cover it in a great detail in next lecture, but let us just touch upon it. So if you people know that there is this issue of memory coalescing with not issue, but there is this memory coalescing that is provided for the DRAM of the GPU. And this bank conflict is something very similar to that memory coalescing thing. But let us understand what is this. So first of all, the shared memory is organized into the 32 banks. So there is something called as bank, and each shared memory has 32 such banks. And if you want to, and if two threads of the same thread block, if they accesses the same bank of the shared memory, then those accesses will be sequential. So let us try to understand this with analogy. So let us say that you are going to some shop to buy some grocery, and if let's say there is just one shopkeeper, then if there are multiple persons going multiple people going into that shop, then since there is only one shopkeeper, each person will be served sequentially. Request of each person will be served sequentially. So here the shop is bank, so there is just one bank, and yeah, that there is only one bank, and multiple requests which are coming to this bank are like that people coming to that shop for buying something. And if that is the case, if multiple people are going to same shop for buying something, their requests will be served sequentially. So yeah, so that is the analogy. So accesses to the same bank will be sequential. But let us say if two threads are going to two different banks for the request, then their request will be served at the same time. So ideally, if two threads go to the same bank for the memory access, then there will be their accesses will be sequential. Their accesses to the shared memory, which is composed of bank, will be sequential. But if two threads go to the different banks, then their memory request can be served parallelly. So I hope this is clear. If there are any questions, then quickly took them. So I think we'll stop here. We'll cover bank conflicts in detail in the next lecture. There are a couple of things related to it, which I won't be able to cover today because we are already out of time. But yeah, if there are any questions, then please feel free to ask them. I'll be there here for a couple of minutes. So yeah. Okay, sir, my question is not related to today's topic, but can you discuss in brief about ray tracing in graphics? Okay, Devyanshu, I'm not aware about this. What is this ray tracing? Can you give some example related to it? I haven't come across this ray tracing thing ever, so it will be helpful if you can elaborate on that. And if I know something about it, then I'll probably take some time out to cover that thing. Or if you are comfortable, you can also type in the chat. Okay, any questions on any of the slides covered today, or any of the material which we covered in the previous lecture or previous to previous lecture? If there are any, then please unmute yourself or just post them on chat. Okay, ray tracing is application implementation level concept. Okay, I am not sure about this ray tracing, but I need to check this out. What is it? And if we'll get some time, I mean, in the later lectures, I'll probably see if I can add something about it.